Hi, I'm Ben-Yaakov. This presentation is entitled A Primer to Precision Rectifiers. Now, rectifiers, diodes, are used in many applications. For example, here I'm showing, say, an AC transformer, a line transformer, and here we have rectifiers which are rectifying the AC into a DC, and which is filtered out by this capacitive filter, producing the DC output here. Now, this is not what we are talking about. We are talking about diodes that are used in instrumentation, and primarily we are talking about diodes which are used for rectification, precision rectification of AC to DC. And here I'm showing an example for such an application that would require a precision rectifier. Now, here we have a AC voltmeter. It's an old version, which has a diode rectifier, has a moving coil instrument or meter or galvanometer, which requires DC for deflection. So we take the AC, rectify it. There is a limiting resistor that is adjusting the current fed to this galvanometer, to this DC meter, and the deflection will therefore be proportional to the AC. However, since the diode is nonlinear, it has an E, and also it's nonlinear in its V to I curve, then the deflection, of course, will not be linear as a function of the AC voltage. Because at very low voltages, you might not have any current, like if it's a few millivolts. And then, if the voltage is, say, 1 volt or 2 volt, you may have a current, but it'll be sort of clipped here, distorted, and therefore only when the voltage is high, you'll be able to sort of neglect the nonlinearity here, and then you'll see a output which is proportional to the input. So for this, we do need a precision rectifier. Now, in the old days, there were no precision rectifiers, and diodes were used. So therefore, you'll find that in voltmeters, deflection type voltmeters, you'll find that there are two scales. There is the main scale here. This is for DC and higher voltage AC. But then there is another scale here for the lower voltage AC. And as you can see, this scale is nonlinear. And for example, let's say this is 1, 2, 3, 4. Okay, this is the scale, the different scales here. And you see that the one is here. The deflection is much smaller, and then it becomes larger here, and then it becomes even larger, and then eventually it coincides with these, because at this range the distortion due to the rectifier can be neglected. So this is the way it was done in the old days. Now today we are using digital multimeters. The display itself is linear. Most displays, and practically all of them, are fed by DC. So we do have to rectify the AC into the DC in a precision way. Let me just mention that this method is not very good because it's temperature dependent, and if you have to be very precise, then you have to sort of match the temperature behavior to some correction. So it's going to be very tricky. And now, again, we'd like to have, in this case, a precision rectification, preferably without any temperature dependence or very small temperature dependence, because the digital multimeters of today have very high precision. We are talking about here, for example, that the last one is millivolts. So we are talking about millivolts, and it can measure AC to the accuracy of a millivolt. So to do that, we need a precision rectifier. Now, the idea of a precision rectifier is to build such a circuit that the behavior of the diode will not affect the output. And here is a very simple example. This is the the simplest precision rectifier. You have a operation amplifier, you have a diode, the feedback is coming here from here, and as you have a AC at the input, you will have, for the positive voltage, you have conduction here, and since you have here a virtual zero between the two input terminals, since the operational amplifier has a very high gain, so in closed loop the potential difference between these two lines is very, very small. So therefore this point will follow the positive voltage. Now during the negative voltage, this amplifier will not conduct, because the voltage that it will develop is negative, and therefore the diode will be blocked, and as a result you will see a half-wave rectification, having an output during the time that the input is positive, and then zero here. This is pretty much following the input. Now let me explain in a sort of an intuitive way how is it that despite the fact that the diode has a breakpoint, it could be 1 volt even, you still would have a very precise output voltage here, starting from very low voltages here, very low voltage at the input. And the reason is the following. Let's go over a sequence in which the input is, say, 0, and then it starts to become positive here, okay? And the question that I'm asking, what is the level of voltage required here, the positive input, for the diode to start conducting? This is the crucial question here. And since this amplifier has a very large gain, could be in the range of 10 to the 5th volt per volt, therefore, if the knee of the diode is V sub D, you need an input voltage which is V sub D over a open loop, okay? In other words, you need a certain voltage that will generate an out. And if the knee of the diode is, say, 0.6 volt, and the gain is 10 to the 6th, we see that you need only 6 microvolt for the diode to start conducting. So this makes it really very, very precise. I'm not talking about errors due to other issues, for example, the offset voltage and offset current or input current, but just the main idea of the precision rectifier. Obviously, you'll have additional errors depending on the amplifier, which I'm not going into it at this point. Now, this configuration is not very good. It has many disadvantages. There are actually 2 main problems with it. Now, for this amplifier, because you feed in a voltage which is plus and minus, you do need here a bipolar power supply, plus minus, okay? Otherwise, you won't be able to feed a negative voltage here. It'll clamp it or it'll harm the amplifier. So therefore, you have now a case in which when the input is negative, this output will swing all the way to the negative rail. This might cause some ringing, and also due to the slew rate of the amplifier, it might cause some delay here, and therefore you might have distortion, especially if you are trying to rectify a voltage of relatively high frequency. So this configuration is really just an idea, but it's not a practical way to go. A better way to go is here, this schematic, this simple rectifier. It's very similar to what we have seen before. The idea is similar, I'll talk about it in a minute. But we have here 2 diodes. This is still a halfway rectifier. In this case, it will rectify the negative going input, and when there is negative voltage here, this is supposed to be positive, and indeed a conduction will commence here. You'll have a positive input, and the output will be now the input times RF over an Rn, of course, with a negative sign. This will be the gain. Now, why is this so? Well, the reason is that as the amplifier starts to conduct, you have a current here. This is the same current going through these two resistors. So therefore, if this is 0, virtual ground, therefore the ratio V out to V in is the ratio between these two resistors. Again, conduction of this diode will start at a very low voltage because of the very high gain of this amplifier. Now the purpose of the second diode is to capture in this case, the positive voltage, and it'll be the negative output, so that the swing will be only to about 0.7 volt when this diode is conducting. It's a small swing here, and then it'll go all the way back. Now, the output of the amplifier, of course, will adjust itself such that during the positive output, here, this is the output, the amplifier will have to have a voltage which is the output plus 0.7, or the break point of the diode, and then during the negative part of the output, it has to be the break point itself of this diode. So this is the basic configuration of a classical half-wave rectifier. Now you can filter out the output and get a DC, and this is done by just putting a capacitor, which is chosen such that the ripple will be per the requirement, and I'll talk about it in a minute. And the idea is again the same, that you have a current that is flowing through here, or I should say this way, during the negative input. The positive input is locked here, and then you'll have an output which is the DC reflection of the AC voltage. Now there are 2 points to consider here. One is the fact that the output now is not going to be, as before, sinusoidal here, but rather close to a square wave. The reason is that during the positive half cycle, the voltage here is DC because of the charge of the capacitor, the filtering of the capacitor, so that output will have to go all the way to the DC. There'll be some ripple here, and then all the way back to the voltage drop of the diode. So this is kind of different from what we have seen before. But there is another point here that has to be taken into account, and it is actually a source of confusion, and I like to clear it up. There is a major difference between this case and this case. And let me clarify. In this case, we are feeding AC here. I'm just showing a transformer. It doesn't have to be a transformer. And then we rectify the AC to the capacitor. What happens here is that the capacitor is being charged, and then as the voltage is larger or tends to be larger than the capacitor, then there will be current. If the voltage, the positive voltage, is lower than the voltage across the capacitor, there will be no current. So if we do an experiment, say a mental experiment, in which we change the capacitor, what we're going to see is the following. If the capacitor is small, then we're going to have a current starting here, going all the way here, and then stopping. This will be the current. If the capacitor is much larger, then we are going to have current only in this section, and there will be no current here, and this section, and this will be the shape of the current. So this will be the behavior of a circuit like that. And the reason for this behavior is that this rectifier is fed by a voltage source. Not so in this case. The rectifier here is fed by a current source in this circuit. Why is this a current source? Let's talk about the negative half cycle at the input, which means a positive half cycle at the output. The current flowing through here is actually determined by Rin, because here we have a virtual ground, so therefore the current here will be sinusoidal, or halfway sinusoidal. The magnitude will be V in over Rin. This is the current here, no matter what you have here, because this amplifier maintains zero between these two terminals. And therefore, here we have virtual ground, and therefore the current is the voltage across this resistor divided by resistance. So this is the current which is pumped in. So therefore, we have now an RC which is fed by a current source. Okay? Now, current, DC current does not flow through a capacitor in steady state. So the DC current will be flowing through this resistor only, while the capacitor will actually carry only the AC component. The larger the capacitor, the smaller will be the ripple here, and of course, if the ripple is large, there will be some AC also through this resistor, and we'll see some AC here. But with a large capacitor, we're going to see a small ripple. So this is a very, very major difference between this circuit, which looks pretty much the same as here, than this circuit. This is a current. This is not a voltage. So therefore, the DC output voltage here is independent on the capacitor. Not so in this case. In this case, the DC is dependent on the capacitor. The larger the capacitor, the larger the DC voltage you'll get. Not so here. The DC depends on the resistor. And therefore, the DC voltage at the output will be V in over Rin times RF, this is the gain, divided by pi, because we have a half-wave rectification. Now, if we have a larger capacitor, the ripple will be smaller on this DC. We have a smaller capacitor, the ripple will be larger. But the DC value depends only on RF and not on the capacitor. Now, when it comes to ripple, let's talk a little bit about the various definitions of a ripple. The formal definition of ripple is the AC RMS divided by DC. That is, you have to take the RMS of this waveform, the riding waveform, that is subtracting from the full waveform the DC and taking the RMS off it, dividing it by RMS, and then times 100 will be in percent. Now, the definition of an AC is, of course, the sum of all the components, the higher harmonics. You have to take the square off and then to sum it up and then to take the square root. Now, in the general case, the ripple, the AC component, is non-sinusoidal, and therefore the RMS now has to be calculated by taking into account all the components, all the higher harmonics. This is the current of the higher harmonic times the impedance of the capacitor, assuming that the AC is primarily passing through the capacitor, and then squaring it and then taking the square root of the sum. So this is really very tedious. Now, a more practical definition of a ripple will be the VAC peak-to-peak over VDC. That is the peak-to-peak here. Now, this is very practical because you can find it out by looking at the oscilloscope and just looking at the peak. Let's turn now to the question of error due to the offset voltage. V offset is due to a difference between two voltages, and it could be in a given amplifier, in a given device, either plus or minus. There's no way to know it because it's a sort of a random error. So therefore, we have two cases here. And since this is a non-linear circuit, the effect of the V offset will be different whether it's positive or negative. Now for a positive V offset, we're going to have the minus input terminal also V offset, which means that there is a current flowing here, and therefore there is a current flowing here, and therefore if RF is equal to Rin, we're going to have twice V offset. If not, then it's RF plus Rin over Rin. Now if the V offset is negative, then the diode is not conducting. In fact, this diode will be conducting because you're going to have here minus, and the only way you can get here minus is by having a current flowing this way. So therefore, the output that you look at is the voltage here, which is V offset. So we see here the nonlinearity of the circuit, and we see that in nonlinear circuits, superposition doesn't hold. Now, what about full wave rectification? The circuit that I've discussed up to now is a half-wave rectifier, and the idea that can be used in order to get a full wave rectification is the following. Suppose I'm using a halfway rectifier like this. We have an output during the period in which you have a negative voltage at the input. Now, if we add this voltage, this original voltage, with a rectified halfway waveform with a gain of 2, that is the amplitude here, it's twice the amplitude here in absolute terms. When you add to this sinusoidal waveform a halfway rectified waveform with this twice than this, you'll get this. That is, here you'll get the original waveform, and here this negative plus twice of it positive gives you again the waveform. So this is an idea that has been used a lot in order to realize a full wave rectifier, and I'm showing it here. So we have a halfway rectifier. So here we are producing halfway rectification, and then we are adding it to the input via a summing amplifier. This amplifier sums up this input from the rectified waveform with the original input. Now, as you'll notice, these two resistors are unequal. If this is equal, I'm assuming that R1 and R2 are equal. And then by having this resistor half this resistor, then the gain here through the here will be twice the gain here, and this will accomplish what we want. Now, what about frequency response? Now, in most cases, the limitation is not the small signal, but rather the large signal response. For example, if we look at the case of a filtered output here, we see that we have swings of the output of the amplifier between the diode voltage minus the diode voltage to the output. Now, obviously, if you're going to have a slew rate to this amplifier, and every amplifier has a slew rate, this will be a limitation, and consequently, we are going to have distortion and error at the output. So the limitation is primarily slew rate, and for good response, you'd like to have an amplifier with a very fast slew rate if you'd like to rectify high frequency signals. Now what about non-sinusoidal waveform? Now in many applications we would like to avoid the DC. For example, in a multimeter we don't want to feed the DC into the AC signal. So in this case we're going to put a capacitor. Now if the signal is non-sinusoidal, then past the capacitor we're going to have AC, of course, and what we're going to see at the output is just this portion here, So it's going to be highly inaccurate when it comes to the value of the input voltage. Now this brings about the issue of RMS. In many measuring instruments, you like to get the true RMS of the AC voltage that you are measuring. Now, if you use a rectifier like this, you get a value, DC, and of course you can calibrate it to RMS if the signal is sinusoidal. And the calibration is that the DC you are getting is the RMS times square root of 2 over pi because of the half-wave rectification, and the RMS is 1 over square root of 2 of the peak. So therefore you can calibrate the output to be for a sinusoidal waveform. But now suppose with the same instrument you measure a square wave. Now the ratio between the DC of the half-wave rectification and the RMS is different. So there will be an error. You cannot measure through RMS if this is the method of rectification. So let me talk a little bit about through RMS. The definition of RMS is the average of, in the case of a voltage, V squared over a given time divided by this period. That's the average of the square because RMS is related to power. This is, say, for the power of 1 ohm over 1 ohm resistor. So in order to measure RMS, you have to perform this operation. There's no escape from it. And for that, you can do the following. You can take first of all, a rectifier, so you'll have only positive voltages. Notice that the RMS of a positive voltage of a negative voltage is the same. This is because you have V squared, so the same power in a positive or negative voltage. So we have a precision rectifier. And then you can use a multiplier to get the square. Once you get the square, you can filter it out for this averaging. And then you have to take the square root in order to get the value of RMS. Well, that's a rather complicated operation. Now, luckily, we do have quite a number of ICs that will do this job. For example, this unit, AD536A of analog devices, this is just one example, will perform this operation that is in fact doing this. And so therefore you'll be able to get the true RMS of a voltage. Usually you like to have a precision rectifier in order to get positive voltages, rather than to deal with a positive and negative voltage, which you can also do in principle, but having a precision rectifier at the front will simplify it. And while we are at it, let me talk about some other issue of RMS, and that is what are you going to do if you have a very high frequency, say microwave, it's microwaves, an error here, and you'd like to measure the RMS of the current, say, or the voltage translated to a current. Well, in this case, the only way to do it is in fact to use a so-called bolometer or bolometry, in which you actually translate the voltage to power and then measure the power directly or indirectly. And one example will be here. We're passing the current through a resistor. The resistor is getting hot, and the temperature will be related therefore to the power. You can calibrate it, and then you measure the temperature of this resistor by a temperature sensor. So this will give you a true RMS of frequencies that you cannot do this operation with today's electronics. Finally, let me talk about single supply operation. Now, this simple rectifier requires a plus-minus power supply because we are feeding here a positive and negative voltages, the sinusoidal voltage. Also, this one needs a plus-minus power supply because during the time that this diode is conducting, we need a negative power supply for this portion here. So there have been many suggestions for a single supply precision rectifiers. Now obviously you need first of all a unit that will have a rail-to-rail input and output. Goes without saying. But then we need a configuration that will not require negative voltage. Now, here is an example. It's one example of some circuit that have been suggested that works in the following way. We have first of all a amplifier here. It's a inverting amplifier section here. And then we have another resistor which goes into this added amplifier, which I'll show in a minute. So idea is the following. When you have a positive input, here is a positive input, this is positive here, and due to the diode, there is no path for the current. So no current can pass here in this direction. Consequently, this amplifier would be locked to the minimum voltage it can produce, which in a single supply amplifier is 0 volt. So this is locked to 0. So the voltage here is like the voltage in the input, so is the voltage here, and therefore there is no difference here, and therefore the output will be the same voltage. So the gain of a circuit like this, which has a resistor to the plus these two resistors, is 1. So we have a gain of 1 between the input and the output for the positive voltage at the input. So what happens when the input is negative? Well, in this case, when the voltage here becomes negative, the output here becomes positive and the diode is conducting. Since the plus input terminal of this amplifier is tied to ground, we are going to have here virtual ground. So basically we are going to have here something like a short between this point and ground. Here it is. So now this point is grounded. The input voltage is fed here to this inverting amplifier. This doesn't make any difference because this is just loading the input but has no effect on the output. So therefore we're going to have an output which is dependent on this ratio. And if R2 is equal to R1, then it's going to be 1 or minus 1. So in this case we're going to have a minus 1. This is the same value resistors. And the same thing goes for the positive. We have to have 1. So in this case we can get full wave rectification with a single supply. Now there are many other configurations that produce a precision rectification. I'm going to show some of them. For example, if you have a moving coil and you like to feed it with a DC, which is a precise reflection of the AC, one way to go is to put here the full wave rectifier at a feedback. And as we have seen, the current flowing here is in fact a current source. And in this case, for example, the current will be determined by the current flowing through this resistor, because this voltage or this point is equal to the voltage at this point. And therefore, the current through this resistor is V in over this resistor. So therefore, you are pushing here current, a constant current. In this case, it's going to be an AC, but since you have a full wave rectifier, you're going to have a full wave rectification as far as the moving coil is concerned. Now, the output of the amplifier will now have to accommodate both the AC component on the moving coil as well as the jump due to the breakpoints of the diode, of the rectifier. So this is a possibility to feed a moving coil meter with a AC source using precision rectification. Another possibility which is related to it, it's not really an electronic component, but let me just add here that in the case of a current transformer, which is used to measure a current, and you have usually a turns ratio of say 1 to n, that's one turn, and then there are many turns here. This is also acting as a current source, because the current here is a reflection of the current here, and the distortion will be fairly small, and you'll get here fairly good, fairly nice full wave rectification. There have been many suggestions, many configurations of precision amplifier that have been published and been used throughout the years, and I'm showing here just one more example. The difference between this and the one I've shown before, this is a full wave precision rectifier, is that rather than having a half-wave rectifier and then adding the input, actually here there's a rectification of the positive and negative half waves, and then adding the positive and the negative via this amplifier. I'm not going into all the details here. I'm sure that you can figure it out by yourself. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.